lecture on general theory of relativity. Last lecture we have covered parallel transport, and today we are going to cover covariant derivative. Covariant derivative plays an important role because it's a way of differentiation in the curved space. So once we have a covariant derivative, we can express the law of physics in terms of tensors in a curved space time. So let's continue with our lecture. So today's topic is covariant derivative. This is a part of course PH4205 at IISER Calcutta. We have seen that the ordinary derivative or the partial derivative do not transform as a vector field. Hence, we have defined the concept of a parallel transport in order to take or drag the vector from one point to another point so that we can subtract one another and define the derivative. So that is what we are going to do. Let TAB be a vector field at a point P is equal to XA. Let Q be the point infinitesimally close to the point P such that coordinate of PA is given as XA plus delta XA, where delta X is a very small quantity. So let P plus delta P be the vector TA parallelly transported from P to Q. Our new differential operator, which is defined as delta A TB, is equal to limit delta B going to 0 1 by delta B of T x plus delta B minus TA plus delta TA. P is equal to XA with our first point, and Q is equal to A plus delta XA with the neighboring point which is very close to P, and then we have a vector field which has a value of TP of XA at the point P and TP of Y at point Q. Now we take a parallel transport, that is we drag this vector TP from P to Q such that its magnitude and direction is maintained, and hence shifted or parallelly transported vector is denoted by TP plus delta TP, where delta TP is a change due to parallel transport. The vector field at Q, and this is a vector parallelly transported from P to Q. We take a difference and then divide it by delta B and take the limit delta B going to 0. In the last video, we have seen that way we have defined the parallel transport is such that the change due to the parallel transport of the vector component is given by a set of connection coefficients and component of T at the position P and the change in the coordinate delta B. This is how we define the parallel transport, and then let's compute this value with respect to TAB that we can easily do using the Taylor expansion, that is TA of XB plus delta XB is equal to TA of B plus dTA by dxB evaluated at x is equal to T into xB. So these are the two quantities now which we have and which we have to subtract and take the limit xB going to 0. So now we substitute back in this equation. We have the delta TA and we have a T of x plus delta x in terms of Taylor series. Substitute in this equation and then we obtain the expression for our derivative. So we have a TA and a partial differentiation of TA with respect to x into delta x. This is coming because of the change due to parallel transport. These two things cancel away and we left with the simple expression, that is a partial differential of a vector field TA at P minus gamma PAB TP delta XB divided by delta XB and take the limit, then these two would and cancel away. We left with expression for the covariant derivative. That is, a covariant derivative of a covariant vector field is given by partial derivative of that vector field with respect to position minus, we have a connection coefficients, taken the dot product with the vector component TP. This is the definition of our new differential operator, and it is called the covariant differentiation with the connection gamma ABC. Now we have seen that the gamma is simply relate or parallelly transport the vector from a point P to Q, and they are the coefficient of transformation. There is no unique way of doing this parallel transport. You could have a non-unique connection coefficient. So this is what is interesting about the differential geometry. You have at present full freedom to choose gamma. So how we should be choosing the gamma? So what is the connection here? So connection is a way of transporting vector field from one place to another, such a way that the derivative can be taken. So our goal is to have a differential operator on the tensor field. For a covariant vector field, it is given with this definition. That is TA delta of TA TB is equal to partial differential with respect to x, and gamma PAB taken the dot product with the TP to make that tensor field. Now we know that this partial differential is not a tensor. That means we need to add a connection coefficient such that this new differential operator, hence we define, should be transforming as a tensor field. So that is our basic goal, is to have a differential operator which behaves like a tensor by adding this suitable term. So that would be the constraint on the gamma. So this gives us the transformation rule for gamma A. So we need to determine the connection such that the derivative operator acting on a covariant vector field becomes a tensor. So let us see how to do this calculation. We have to derive a transformation for gamma such that our differential operator forms a covariant tensor of rank 2. It's a bit of a long calculation. The general relativity is all about long calculation, so this need to be done. Let's go the step by step. Here idea is we are doing a coordinate transformation from xa to x prime a. Then we are transforming these quantities and then making sure that our new differential operator is transforming like a tensor, and then we'll see whether we can get a constraint on the transformation of gamma ABC. So let's start with the covariant differentiation on a coordinate system x prime a. So this is what we have, nabla prime acting on the t prime. So this in that coordinate system can be written as a partial differential of a component of t prime b with respect to coordinate variable, that is x prime a. Then we have a connection coefficient in that coordinate system, which is gamma prime with the 3 indices to that. And then we have a tensor component of TP. This is the basic definition of a differential operator, which should be valid in each and every coordinate system, whether it is x prime or whether it is x. So we start with the x prime and do series of coordinate transformation and come back to the coordinate x and see whether it also follows the same definition of covariant differentiation, and then we can put the constraint on gamma such that these two definition of a covariant differentiation remains form invariant in both coordinate system x prime and x. Now first thing is the covariant vector t prime itself transform with the following transformation rule. T prime a is equal to dxb by dx prime a into tb. So this is the standard transformation rule for the covariant vector field, which we have seen several times. We substitute that in our equation. So we have this partial differential where we have t prime b And in this contraction with respect to gamma, we have another T prime V. We substitute both in terms of coordinate xa. So as a result, we get dx prime a of dxq by dx prime b into tq minus gamma prime p upper index and b a are lower index, and then we have dxq by dx prime p into tq. This is just substitution of this transformation rule for t prime into our definition of a covariant tensor in the x prime coordinate system. And then let's expand this. We'll expand the first term. This we have done earlier. We get two terms. First term which transforms like a tensor, and then remains a term which do not transform like a tensor. And then the second term remains same. Of course, we have to do some adjustment of indices. We again use the chain rule, and then we simplify this expression. So again, we use the chain rule as we have done earlier. We replace del tq by del x prime a in terms of del xq by del x prime b into dtq prime by dxp. And then we have these two terms. One we know do not transform like a tensor, and one which we do not know how it transform at all. So let's combine these two terms, and we notice that it has a same vector component tq as a common term. We pull it out and write these two terms, which we somehow have to get rid of if this has to transform like a tensor. If the covariant differentiation as defined above have to be transformed like a second rank tensor, then it should follow the following rule of the tensor transformation. That is, now simply look these two indices as a covariant tensor of rank 2. Don't worry whether it is a differential or whether it is a vector component. And then we assume that it transforms like a second rank tensor. Then the transformation rule would be del xp by del x prime a, del xq by del x prime b into delta p delta q. This is just the rule how the second rank covariant tensor has to transform. And then if it has to be same from the both frame, then these two expressions will have to give the identical result. That means once we transform both right hand side and left hand side to the new coordinate system from x prime to x, then they should be same if they are both satisfying the tensor transformation rule. Now again we express the form of the covariant differentiation. That is, we have a covariant differentiation here in the coordinate system xa. Now we know that the covariant differentiation would take this form, and then we substitute that in this, and then we obtain the expression for the covariant differentiation in the coordinate system xa. That would be the first two terms are the transformation from x prime to x, and the second is a definition of a covariant differentiation itself in the x coordinate system. Now that has to be equal to the one which we transformed expression from the x prime system. So now these two have to be equal if our derivative operator is a covariant derivative. Now we just play around with the tensor indices. That is one of the common exercise in the general theory of relativity. It is said that the relativists do their exercise by raising and lowering indices, not by raising and lowering their hands and legs. Let's expand this term. So we have first term simply multiplication. There is no big deal about it. This two get multiplied and this term get multiplied by this. And the same way we have these three terms here. We'll have to combine all of them and then cancel the relevant terms and see what does remain. Now it is straightforward to see that these two terms are same, and then they would cancel out. And let's look at the remaining terms and see whether we can do something about them. Let's first rearrange this term. Let's take this term, that is basically a transformation rule for the gamma prime is involved, which we do not know and we want to find out. And all other terms we keep. This is the original gamma, which is in your coordinate system x. So let's keep this all. So this is a term which is a bothersome term that we write it here, and this is a term coming from the our x coordinate system, and this is a term which comes from the x prime coordinate system, and this gives us the relation between the gamma in the x prime coordinate system and gamma in the x coordinate system. Now once we write this down, we see that the TQ is coming as the same factor. Of course, we have adjusted some indices to get that. You figure it out yourself. Since TQ is an arbitrary vector field, there is no need to be specific about it. It could be any field, and then this relation should be valid. That means we simply get rid of this TQ, and then we get an expression that the gamma prime in our x prime coordinate system with some differential, and then gamma in terms of x coordinate system. Again, this bothersome term is still remaining. We somehow have to get rid of this. On the other hand, there is also this term which doesn't look very pleasant there, because we just want the coordinate transformation rule for this. So we have to get rid of this. But we know very easily how to get rid of it. That is by multiplying by the term dx prime s by dx q. So once we multiply this both sides with this term, something interesting happens. So here it is a contraction between the q and q. That is how we have arranged. That means this is basically a chain rule, and the same thing would happen. In this case, we see that some of the indices have to be rearranged. There is no need to anything very serious, and then we left with this term. Now, after some simplification, you see that one is a chain rule that results in a term like dx prime s by dx prime p, which is basically delta s by p, and that would simply change your p index to s index. That is all this term does. So that is a trick which we have used, and then we are left with this term. Essentially looks like a transformation rule for a tensor. So this is what do we have? Essentially the gamma need to transform with this expression in order to be our covariant derivative to be invariant under the coordinate transformation, or in other words, the so-called our covariant differential operator, if it need to be tensor, then our gamma need to be transformed like this. In our earlier derivation, you might have seen that the transformation rule which gamma need to satisfy is somewhat not tensor-like, because there is a tensor-like transformation and there is some extra term. It is the same term, same bothersome term which came from the transformation of partial differentiation. That means gamma itself is not a tensor. This is a transformation rule we have derived. We see that this is transformed like a tensor which has two covariant indices and one contravariant indices. That is why it is represented by gamma QPR. But there is this term which is, there is no way to call it a tensor transformation of anything. So this makes it our gamma is not a tensor. It should not be surprised. Let's look at our definition of covariant differentiation. We have three terms. The first is a partial differentiation, which we have seen is no tensor. And then we have a covariant differentiation. We want it to be tensor. That is very important. Otherwise, all the exercise which we are doing is fairly useless. Then we have this transformation for gamma. Certainly, this not be tensor. What really happens here is that when we transform the partial differentiation, there remains some terms which are not tensor-like. So does when we transform the connection. When we transform a connection from one coordinate system to another coordinate system, we would be left out with a term which do not transform like a tensor. Now, what happens is when you subtract one from another, those two non-tensor terms get cancels out and you would left the difference, which remains to be purely tensor-like. So difference between the two non-tensor need not be always tensor. However, in this specific case, we have defined non-tensor quantity such that their difference is always forming a tensor, and that is what we exploit to define covariant derivative using a non-tensor nature of a connection coefficient. Of course, all these things we have done, we still don't know what is gamma. Gamma simply is the coefficient which drags the vector component from one place to another place in the space-time derivative of a contravariant vector. So we have seen that covariant differentiation of covariant tensor is a second rank covariant tensor. So that we have seen using the transformation property. The covariant differentiation hence obtained has a following form. Now let's look at the scalar. Scalar is transformed very easily and whose differentiation giving rise to a vector that is a covariant vector of a rank 1. Now, can we also do a covariant derivative of contravariant tensor? Of course, you can do whole exercise what we have done for the covariant derivative. We can also do it for the contravariant vector and then show that there is a differential operator. Now, question comes is whether it is the same differential operator or not. There is a shortcut. Shortcut also means that it is a bit of an obscure. So there would be always some doubt lingering back of your mind, but that is a way you can understand. By clearing those little doubts, you can always get a better understanding of the subject. Let's construct a scalar f by contracting the two vectors. GAB upper is equal to TA UB, it should be UB, and then that also can be written as a T upper A and U lower A. That is T upper A and U lower A. So this is how we have connected the covariant vector and contravariant vector. We can use a metric tensor to raise and lower the indices. Now let's take a differentiation on both sides. Now one side you have this differential. This differential for the covariant differentiation for a scalar has to be simply partial differential. There is gamma plays no role because partial differential itself transform like a covariant vector. So there is no problem here. So but look at this. We apply the product rule. Then we see that this particular thing would be split into two terms. First one would be UQ del A TQ and TQ del A UQ. So this is simply coming from expansion. All the differential operators should follow the product rule and the covariant differential operator is no exception to this. So it has to simply expand this. That is what we do. And then we already know how to expand this in terms of gamma, and then this we have to write in terms of gamma. So that is a goal. So since we already know how to express this, we keep this term as it is, as we have done for the finding of the transformation rule for gamma. Here also we do the same thing. We keep this as it is and then later find out what should be that. Let's look at it in a slightly different angle. This is a partial differential. Again, we write it in terms of partial differential of this vector field. And then we can simply expand the partial differential product rule. Now it should be true because this is just a scalar which we are handling here. This should be basic properties of the partial differentiation. So we simply apply the product rule here too. Then you see that the first one is a partial differential of T and multiplied by Q, and the second become partial differential of Q multiplied by P. There is no need to worry about order which we are right. Now we compare these two equations and we can come to the conclusion what do we want. So simply compare them and get rid of all the common terms. In addition, this property should be true for arbitrary vector both T and U. So let's assume the U is an arbitrary vector and simply get rid of it as we have done earlier, and then we end up with the definition for the covariant differential of a contravariant vector. Note the sign. Sign changes from the covariant vector to contravariant vector. If you are unsure of this shortcut, you can actually do the long calculation as we have done for the covariant vector. You can do everything and you realize that that would have a plus sign instead of negative sign. I can leave that as an exercise. You can do it, or maybe I can give it in the exam next class test for you to do it. Now it is easy to show that it is a second rank tensor of a mixed ranks, one covariant and one contravariant. So this is how we define the covariant derivative of a contravariant vector in terms of gamma, which we really don't know what it is. We have done through all sort of calculation assuming abstract properties of gammas, and we have not yet bothered to exactly calculate what it is. That is an exercise by itself. We will do it sometime in the next lecture. Now here is a problem 2 of a homework 2. Derive the transformation rule for the connection gamma ABC under an arbitrary coordinate transformation and show that it is not a tensor. Deadline for this is 7th February 2021 at 6 p.m. You can submit it on VLearn. This is the second problem. First problem has been there in the 2 lectures behind, that is on the 7th video. You would see that problem number 1. So these 2 problems you will have to submit by Sunday, 7th February. Let me stop here and continue with the Riemann geometry in the next video.